Okay, very good morning to you. So today we are going to discuss one of the very important topic in diffusion. Nothing but diffusion, the Fick's law of diffusion. The Fick's law of diffusion. Now, the Fick's law of diffusion is the Fick's law of diffusion is applied to evaluate the diffusion process. Now, for example, in many of the industrial applications, we are very much interested to know how fast the diffusion process occurs or the rate of the atomic transfer or the rate of mass transfer. So we can see the diffusion like this. The diffusion is the quantity of an element that is transported within another element or material during a specified period of time. So this is just like a small example, an schematic diagram of a diffusion process is pasted. Here you can see that a gas diffusing through a metal plate. You can see the gas pressure PA at one end, and once it is diffuses through a unit in a cross-sectional area A, and this is the diffusion direction of the diffusion of gas species, and you can see the gas pressure at gas at pressure PB. So at both end of the metal plate, the pressure will be different. It is well known that the PA will be always greater than PB. So this we can see the diffusion process in this way. Okay, so as I told you, the diffusion, we need to evaluate the diffusion process. This is very important. So in order to evaluate the diffusion process, it is useful to know how fast the diffusion occurs or the rate of mass transfer. And this rate is expressed as, we already familiar with some of the terms associated with the diffusion. In the last few videos I posted in your Google Classroom, you can see the definition of terms we explained. So the term which is associated with the rate of mass transfer is diffusion flux J, isn't it? So the rate is expressed as diffusion flux J. What is diffusion flux? Do you remember? The diffusion flux, yeah, the mass flow per unit area per unit time is known as the diffusion flux. What is called mass flow per unit area per unit time? It's nothing but the mass of diffusing species which is passes through the unit area of cross section, or the number of atoms which is diffusing through the cross sectional area. So usually the diffusing species will diffuse through and perpendicular to a unit cross sectional area, as like shown in this figure, isn't it, per unit time. So I can express the diffusion flux like this. You can see the expression diffusion flux J is equal to mass flow divided by area into time. So J is equal to M. So mass flow I will represent it as M divided by area A into T. Now let's move on to so here the A is a cross sectional area through which the diffusion takes place, and T is the time elapsed. Okay, now let's so if we are going to express it in a differential form, we can express like J is equal to 1 by A into dm by dt. So if this is the same diffusion flux, we can represent in a differential form by changing diffusion flux J is equal to 1 by A into dm by dt. So we can represent it like that. Now let's move on to the Fick's law of diffusion. There are two laws associated with the diffusion process. One is Fick's first law and the Fick's second law. The Fick's first law is based on steady state diffusion, whereas the Fick's second law is based on non-steady state diffusion. Yeah. Now let's move on to the Fick's first law for steady state diffusion. Now, when the diffusion flux does not change with time, that is steady state diffusion, isn't it? We already seen what is steady state diffusion and non-steady state diffusion. In steady state diffusion, the diffusion flux does not change with time, or the flux at any cross-sectional plane along the diffusion distance remains constant. Whereas in the case of non-steady state diffusion, at I mean at any given instant, the flux at different cross-sectional planes along the diffusion directions are not equal. So here we are going to discuss about the Fick's first law for steady state diffusion. When the diffusion flux does not change with time, or when the number of atoms transported through the area at any instant is same, a steady state condition exists. So when the steady state diffusion in a single direction is assumed, the flux is proportional to the concentration gradient. So during steady state diffusion, the diffusion flux is proportional to the concentration gradient. So you can write J proportional to dou C by dou X, or I can write J is equal to minus D into dou C by dx. We also seen this term. The term is nothing but the diffusivity or the diffusion coefficient, isn't it? What does it? What is a diffusion coefficient or diffusivity mean? It is an index of the rate or intensity at which the atoms diffuse. The rate at which atoms diffuse, or the intensity at which the atoms diffuse. So it's an index. So this is a constant, so that is diffusion coefficient. Then why the minus sign is shown here? Minus sign, I mean the negative sign indicate that the mass flow is always taking place from high concentration region to the low concentration region. Okay, so hence you can express the first law of diffusion as, we have already seen J is equal to 1 by A into dm by dt when it is expressed in differential form, 1 by A into dm by dt. So I can express J is equal to 1 by A into dm by dt is equal to minus D into dou C by dx. This is an expression to for Fick's first law for steady state diffusion. Now let's move on to Fick's second law. It is based on non-steady state steady state diffusion. So what would be the non-steady state? If we have seen the steady state diffusion is nothing but the flux does not change with time, or the number of atoms transported through the area at any instant is same. That is was steady state. In the case of non-steady state, as the name implies, at any given instant, the flux at different cross-sectional planes along the diffusion directions are not equal. And which means if you take this thin plate, and if you take, if I am going to classify the entire thickness into T1, a cross-sectional plane, different cross-sectional planes, and if you take the flux at the different cross-sectional planes along this direction are not equal. Or in other words, the flux at a given cross-section is a function of time. So that is Fick's like second law for non-steady state diffusion. So at any given instant, the flux at the different cross-sectional planes along the diffusion directions are not equal, or the flux at a given cross-section is a function of time. You can see a thin metal plate. You can see this is a unit area, and this is a flux in Jx. This is the input, and this is a flux out, Jx plus delta x, where the thickness is delta x. You can see this is a here we are considering an elemental volume of length delta x. Along this direction the diffusion takes place, and a unit cross-sectional area, you can see it here. And what would be then volume? If this is a unit cross-sectional area and this is the length, or length along which the diffusion takes place, and if this is a length and this is a unit cross-sectional area, unit cross-sectional area means 1 into delta x is the volume, isn't it? The volume of this element, 1 into delta x or delta x. Now we need to find out, or we need to evaluate the diffusion process. For that, we need to find out the rate of accumulation or depletion of the diffusing species within this elemental volume, which means we know that there is an input, there is an output from the elemental volume, and how much diffusing species is accumulated. Okay, in order to find out, so that is we can write it like the dou C by dou T into delta x. I mean dou C by dou T with into delta x. So I can write, I can express the same in a differential form. I mean the difference in flux in and out of the slab. I mean the rate of accumulation or depletion of the diffusing species can be expressed as the difference in flux in and flux out. It is inbuilt, isn't it? The difference between the flux in and flux out is nothing but the rate of accumulation. So dou C by dou T delta x is equal to jx minus jx plus delta x, because this is a high concentration region, this is a low concentration region. So jx minus jx plus delta x. So I can write jx minus jx plus dou j by dou x into delta x. I can write it like this. So this jx gets cancelled. So I can write dou c by dou t delta x is equal to minus dou j by dou x into delta x, and this delta x gets cancelled, and so I can write dou c by dou t is equal to minus dou j by dou x. You can write this as expression number 1. Now we're using the first law, we know that j is equal to minus d into dou c by dou x, isn't it? If you substitute instead of j this expression, I can write dou c by dou t is equal to minus dou by dou x into minus d dou c by dou x. So I can get d dou square c by dou x square. So dou c x by dou t is equal to d square cx by dx square. Okay, so where here Cx is the concentration of the diffusing species at some distance x from the surface. The concentration of the diffusing species at some distance x from the surface, and where t is a time is in time in seconds. Okay, so we have, so the Fick's first law and Fick's second law, these are very important topic under diffusion. The Fick's first law is based on the steady state diffusion, that is the diffusion flux does not change with time, and the Fick's second law is based on non-steady state diffusion, that is flux at a given cross section is a function of time. So we have seen both the expressions. So these equations of Fick's law, I mean Fick's first law for steady state diffusion and Fick's second law for non-steady state diffusion, is used in the analysis of various transformations and heat treatment process applicable to engineering materials. So you can find the application of these laws of diffusion in the heat treatment process in order to evaluate the diffusion process. We use this Fick's law. Thank you.